Hello, everyone. Let's turn our attention on today's lectures on linear regression as a part of the time series analysis and forecasting series of lecture we have. But this is the first Jupyter notebook we have. We're going to go through some very easy, straightforward method for doing linear regression, which frequently we use in the time series analysis. So here what we have is, for example, we have example of regressions on the weight of the car, the horsepower of the car, and there's mile per gallons fuel efficiency, and see if we can find out the relationship between them. And also, example like we want to predict students' exam performance index or score based on the number of hours they study. We observe that the students study more hours, their score goes up. An example of the prediction of the exam scores. So this is another example, but we understand that for getting a good grade, good exam score, number of hours of study, it may not be an only factor. For example, other is how much you sleep. Do you have sleep enough the night before the exam? And what kind of extra curriculum activity you involve, for example. And other factor, can they also impact your exam score? So this is a very interesting example. We got it from the Kager's data resort, and we can later on to perform a so-called multivariate linear regression for them. Okay. And in our example, there are two different type of variables involved. The first one is the so-called our study, and we call it independent variable. These are the factor actually we can control or observe directly. Okay, so this is what we call an independent variable. The second we call a dependent variable. Usually we use as an output or performance. For example, in this example we use is the exam score or performance index, because it depends on how many hours we study or other activity we involve. So we use the independent variable to predict the dependent variable. Mathematically, we can also represent this. The y is our dependent variable, and x is our independent variable. So we're trying to find out the relationship between the y and the x. And general form is beta 0 plus x times beta plus epsilon. Okay, the beta 0 right here represents the intercept, the constant intercept. Beta is the slope of each one of the independent variable. Finally, the interesting is the epsilon. Epsilon is representing the arrow, model arrow, which the model cannot explain by this linear relationship. And we're assuming if the model is correct, then the epsilon is supposed to represent supposed to have a normal distribution with mean of zeros and with a standard deviation of sigma. Depends on the property of the sigma. We currently can have several classes of the linear regression. And the first is a generalized least square for arbitrary covariances. Okay. So here, the generalized linear least square method, we don't assume the independent variable are independent. Okay, the ordinary least variables are least square method. We're assuming the arrow terms and its corresponding covariances term are identical, independent identical distributed. So that means there's little or negligible relationship between the independent variable. Okay. The third one is a so-called weighted least square, which is we can weight each one of the variable based on pre-knowledge. Finally, is another least square method we consider so-called autocorrelation and arrows. So that means the independent itself has an autocorrelation among themselves, and see if we can model that. But today we're going to focus on the second one, is the ordinary least square method, and we see how easy we can implement this quickly. There are two different Python libraries we need to install. The first is the scikit-learn library, which is you can install either using conda install scikit-learn, or you can using the pip install. Okay, the scikit-learn library is a machine learning library frequently used. We also in the field. Okay, and throughout the semester we will be cover this frequently using some of the machine learning algorithms scikit-learn provide. The next is the stats model library and it's a statistic analysis library from Python. It's very popular use, especially for time series data. You can install these by conda install stats model or pip install. Just uncomment the line you want and you can install them. Here we're going to show you a really simple method to perform a least square method. Here we're going to use, other than NumPy, Matplotlib's library is for the visualization, and Panda is for the data set. Okay. Here, the only thing we use is the scikit-learn linear model, linear regression. Okay. So here we're going to do this. The next, we're going to read in the data file. We'll call it regression data. This is an example. Okay. And here, after we read in, we change the column names to exogenous variable and endogenous variable, so you can see that. There are total 100 rows separated into exogenous variables and endogenous variable, and which is our x and y. Okay, and we refit it into x and y, for example. And then we can see that x and y both are the Panda data frame right now. And we can use the x and y to run the regression model from the scikit-learn. So it's simple. Just create a model called linear regressor, and based on the linear regression function from the scikit-learn, then we just fit the data x and y in the linear regressor. After that, we can perform the prediction for x, put in x, and we get a y prediction. And we can see the visualization afterward. The scatter portion, the blue dots right here represent the original x and y data. And the red line represents the x, and the corresponding y prediction is a straight line, so we can show that easily. If we were just interested in the plot, we can also using the Seaborn library to plot. And this is a visualization package based on the Matplotlib. So here we're going to only import the Seaborn as SNS, okay? And then we can directly using the regression plot. Okay, using the regression plot, the x equals to the data for the first column we call the exogenous variable, and the endogenous variable equals to y. All right. Here you can see that I'm using the I location to indicate the first column and the second column, column 0 and column 1, and to plot it. And even give you a 95% of a confidence interval for the entire regression line. However, this method is good at the visualization, but not necessarily good at giving any of a detailed regression result. So here, up to here, we only spent about 5 or 6 lines of Python code. We already can perform a linear regression. So other than that, I'm just icing on the cake, adding other method to show you how to do that. The third method is using the polynomial fitting features and the linear regression fit for getting the fitting the data. So here we're going to illustrate the scikit processes. I'm going to do a polynomial fit for that, a feature for that, and then using the linear regression. So I'm going to first giving a polynomial fit of a degree of 2, which is a quadratics right here. And then we're going to fit the transform. And here we get a x polynomial fit, and based on the polynomial fit we have. And then use that to perform linear regression. So here what we do is we convert the x itself based on the linear second degree, which is quadratic polynomial fit right here. And then we move on to the x pod, okay. Then we're using the x poly, which is polynomial after fit, and as independent variables to fit y. So here you can see that the original data in blue, the polynomial fitted data in the orange. So these will be giving you features and the same manner for example, your model may not be linear regression, and maybe a nonlinear regression or polynomial regression. So this is one extra step for perform nonlinear regression. So here is very simple, just using the polynomial fit, determine what type of degree you have. And frequently, if you just plot the cluster, this is not very obvious. For some other data, you could visually see that they have a nonlinear relationship between independent variable and the dependent variable. Here, and then you can choose the degree of polynomial fit you want, and you perform nonlinear regression. All right. Next step is see if we can use the STES models API, ordinary least square method, to perform a linear regression. And this is a more formal method to perform linear regression. So first we import the STES model API as SM, and we're using some of the so-called sandbox regression pretest. Okay, if we want to add a constant, we can add a constant using STES model API add constant to perform. So here we will directly adding a constant terms in the x1. We'll show you later on. And what is this add constant? Basically adding dummy columns in the x and using that as a so-called intercept, which is the beta 0 we have in the generalized model. We have the beta 0 column. So this is supposedly straightforward. And I'm just showing the type of data we have is a panda series in this case. Then we're using the endogenous variable as a y, exogenous variable as a x to fit. And here is the fitting without the intercept. And well, you can also using x1 to fit, since I add a constant to it, so that's the intercept. First we tried the one without intercept, see what happened. We can run this few together. X is not defined. Okay, now we can see that we can fit the model without the intercept, and which gives us roughly 98% of R squared, which is exceptionally good on this method. And you see that we have a total 100 data point. We have one endogenous variable x, one exogenous variable. Okay, and giving you the coefficient for the exogenous variable, and give you the t statistics and the probability of basically the probability of the data is greater than p. The test is greater t statistic. Okay, so it's probably 0%, meaning this particular coefficient is significant, and this is the 95% of a range for the exogenous variable. And give you a whole bunch of performance index right here, and we will explain this later on, and when we're dealing with more complicated regression problem. So here we can also print it out the parameters, which is 1.4795, and you can print out the R squared value right here individually. I'm just showing you it can be done. Okay. So here we can also using a, we can come back to common out and change this to using an intercept. Okay, and rerun the model, see what it is. And you can see that with the intercept, which is we're using x1, after adding the constants in there, the R square value from 98% reduced to 60%, around 60%. Okay. So actually the model is better without the intercept, without the constant term. Okay. Next, we're going to illustrate if we can use using other method to do the same thing. So also using statistic models, formula API, ordinary regression. So here is the same thing. We first look at the X, which is the panda data frame. Then we determine a model, run the model real quick, use SM1 and formula, and what I'm trying to say is y to x, which means is how much is that for x, okay? Y is relationship to x. And data is the df1, which is x and y column we have, and we'll print out the summary, okay? So this will give you, And also we can plot it out both with or without the constant term and see how they fit. The pink dot right here represents the original data, and the green line is with the intercept, and the orange line represents without the intercept terms in our model. All right. The question is, why are you using the second ordinary least square methods and for doing the same thing? This portion I want to extrapolate the concept of linear regression and using a so-called generalized linear least square method for the nonlinear parameters, okay? So here is we have a nonlinear curve, but the linear is but linear in parameters. So see what I have. So I'm simulating a curve. First, simulate curve. I'm using 50 samples, and significant is 0.5. I'm using a constant line space between 0 to 20. Total taking 50 sample. Okay, so I'm going to create another stack, which is the sine wave, okay? So x2 is the x variable, and this part is the y I'm creating. And here, second term of y is x minus phi to the square. So here I have original x2, sine of x2, and x2 minus phi to the square, and then I have a constant term is 1. Okay? So I have assuming a beta version. Okay. We have 50 sample, and the beta right here represents the weight of each one of the independent variable. Here I have 4 type of independent variable. Let's repeat again. x2, which is the original line space, so I'm generating. Second is the sine wave of the x2, okay? The third is x2 minus phi to the square, okay? Finally is just 1, okay? Just fully 1. And each one of the x square, I give him certain type of weight on that, which is 0.5, 0.5, negative 0.02, and then phi. So I'm using this to create a synthetic data point, which is we'll call the y true equals to the dot product of x2 times the beta. So basically is the y I'm going to use. And the y2, which is our dependent variable, equals to the y true plus certain normally distributed random noise. The random noise, the standard deviation is 0.5, and this is random normal, so the average or the mean should be 0 in this case. So here I can print it out, the y and y2. Okay, so here this is fairly straightforward, and I can also, using the ordinary least square method for this nonlinear relationship, trying to figure out the y2 relationship towards the x2. So here where we have, I'm getting 95% of the r squared up here. Okay, total 50 data point, and then I have 3 independent variables other than the x2 itself, and the sine of x2, x2 minus phi to the square, and so on. So I have 3 of those, x1, x2, x3, basically. Then I have a constant term, okay? And you can see that from the p-value, which is the probability of this number greater than the t-statistics, okay? The probability this number come out of this t-statistics, though the possibility is almost zero, so which means all the terms x1, x2, and x3 and the constant terms are significantly important to the model. Okay, now it's time to basically showing the parameter itself, okay, which is listed right here, okay. And then the standard error, okay, 0.0225, which is the standard error right here, the second column. And then is the predicted value, okay, for these 50. Finally, we can plot the result and to see how it works. So I'm going to plot x2 itself against y2, which is the y true plus the random noise. So here we have is the data itself using the dot is basically the the blue ones are the true value. The true value is the blue line. So the data itself is the blue dot, okay? The ordinary least square model is the dot with the red line. And you have a lower and upper bound for this, which is the confidence interval, 95% of confidence interval for this nonlinear least square method. So here I'm just using a synthetic data, simulated data, for a multivariate linear least square models right here. So here so far we learned the straightforward linear regression using one independent variable, one dependent variable, and see if I can using a polynomial feature first to fit our x and then run into the least square linear regression model. Third is we're truly using a generalized or ordinary linear least square method, but with the nonlinear possible data. Okay. Next subject I want to discuss before we go on to a multivariate least square model is sometimes you say, hey, many times the least linear regression model may not be the perfect fit, since our data could have present a so-called curvature type of as phenomena. So here is the two solution we have. One is the polynomial features. Second is using a generalized ordinary least square method to fit it with a nonlinear curve. See how that happens. And giving each one of the parameters certain weight. All right. So here is I can increase the number of the polynomial features in higher degree, as quadratic, cubic, and so on and so forth. Or I can increase many of the curvatures or the nonlinear relationship for our x. So this creates a problem. Can I increase the model complexity and getting a better R-square value, higher R-square value? And this is really a better model? And here is the discussion about underfit and overfit, assume. Okay, here is the things I want to illustrate this concept. So here what I have is using the same set of data and trying to fit with increasingly higher degree of freedom. For example, now I'm trying to do is just a simple cosine function X is my independent variable, and cosine function is 1.5 times pi times x. Okay, so I'm going to return that. So I'm going to manufacture this data again as an illustration. So I'm trying to do is using a synthetic data. And I'm going to try the polynomial fit with the 1 means linear relationship. 4 is the degree of 4 and degree of 15. And total sample, I'm using 30. I'm creating X based on the random sample, which is uniformly distributed. Total sample 30, okay, and I'm going to sort them. So these independent variables are not even least space. It's not even evenly spaced. It's random uniform. And I just sort it in ascending order. The y is manufactured in a way as using the function I have, the true function I have is a cosine function transform and plus a random normal. Okay? Example. So here I have a random normal, number of samples 30 plus times 0.01, which means I assume the standard deviation is 0.1. Then I'm going to plot it out, see what happened.